Okay, there it goes. All right. What we want to talk about now is, what if you have a graph? What if you have a graph and it kind of comes, you know, something like this. And it's a very irregular shape, all right? And this is pretty irregular. So how do we figure out how much area is under the curve? Because it turns out that the area under the curve represents things in terms of a physical sense, right? So when you're looking at, for example, a position graph, the area under the curve is your displacement, all right? Your total displacement, how far away you are from where you started. So the area under a curve has a lot of physical, real-world meanings when we look at things. And we'd like to be able then to calculate the area underneath the curve. This was the second major problem that led to the development of calculus. The first being, how do you quantify instantaneous velocity? Because in an instant, there's zero time elapsing, right? And so normally, velocity is the change in distance divided by change in time, but if there's no change in time, how do you do that? So that's when they created the idea of the limit, all right? So the limit came into being, and because of the limit, they were able to quantify exactly what they meant by instantaneous velocity, the speed at precisely one moment in time. The second problem that led to the development of calculus was this. If you have an irregular shape, and it's not a rectangle, it's not a circle, how are you going to calculate how much area is underneath it? And again, it's the idea of the limit that makes this possible. So what they do is they create a partition of this shape, or this space. And by a partition, we mean to cut it up into parts, all right? So typically you want to know what the area is under the curve between two x coordinates, a and b. That's our typical way of saying it. So in other words, if I were to draw a vertical line at x equal a and another vertical line at x equal b, how much area is underneath here, right? So we're looking at the area that's under that curve. How many square units in it is it? Now keep in mind that a square unit is literally this 1 by 1 square, right? That's what we mean by 1 square unit, all right? So the question is, how many of these 1 square units can you fit into this region here, all right? So we're trying to figure out how to do that, and this took centuries, right? I mean, they could not figure out how to do it because you could have all kinds of different shapes. They wanted a method that worked no matter what the curve looks like. And that's a problem because, yes, you can come up with a method for a particular curve, but then you can't necessarily use that method on a different shaped curve. And they wanted something that worked on all the curves. So what they came up with, and of course this has been around for millennia, all right? The Chinese have been doing this for 5,000 years. They decided they would cut it into a partition, which means cut it into parts, a regular partition, like a regular solid where all the cross sections are the same, a regular partition, they're all the same width. So what they did was they said, okay, I'm just going to divide this up into regular little slices like this. Now if you're dividing them into regular slices where they're all the same width, how wide would each one be? If this is A, and this is B, how wide are they? 1, 2, 3, 4, 5, 6, 7, 8. How wide are they each? Divide what by 8?
A to B.
B minus A, and then you divide by the number that you have in your partition. So this is the width of a regular partition. You take the length that you're trying to find the area under, B minus A, and you divide it by the number of partitions, the number of cuts you made, all right? Now, this is how wide each box is going to be. But the next thing they had to do was deal with this irregular top. If it's not a regular geometric shape, we don't have a formula for it. So they started with the easiest geometric shape that they could create out of these, which would be a box or a rectangle. Now, to make it uniform, they started with a left-sided box. And this is called a left Riemann sum. I think it's two ends. All right? What do we mean by a left Riemann sum? They went to the left side of each partition, left side of each rectangle, and they put a dot there at the height of the function on the left side. And they drew a horizontal line to the next partition line. And they created a rectangle. Does everybody see that rectangle? Now, how would you compute the area of this rectangle? What's the area of a box? Length times width, right? So what's the width? The area of box 1 is delta x times what? If this is my function f, what is that right there? F of a, isn't it right? It's the y value. It's the y value at that x coordinate. So this ends up being delta x times f of a. Well, then they went to the next partition. Again, to be uniform, they took the left side of the box, made a dot there, and went across, and that created the area of the second box. What would the area of box 2 be? Delta x. What's the coordinate for the fx coordinate right here? It's not a, it's a plus delta x. So this spot right here is a plus delta x, so the next one is f of a plus delta x. What about the third box? What's that x coordinate right there? Yes, go ahead and say it, a plus 2 delta x. What's the next one going to be? A plus 3 delta x, a plus 4 delta x, a plus 5 delta x. What's the last one going to be over here for us? This is going to be 1 delta x, 2, 3, 4, 5, 6, 7. 7 delta x is the last one, right? Does everybody see that one? So this is going to be a plus 7 delta x. How does 7 relate to the number of boxes? We said there are 8 boxes in what I drew. Do you notice that 7 is 1 less? So on a left Riemann sum, the last one is going to be at n minus 1 delta x. Because the first one is at what we call x sub 0, meaning I haven't moved across any partitions yet. So we would call this x0, x1, x2, x3, x4, x5, x6, and x sub 7, right? These are subscripts, right? So basically you continue in this pattern until you get down to your 8th box, which is delta x times f of, oops, parentheses in the wrong place, a plus n minus 1 delta x. And then what do you do to estimate the area for this curve? Now notice that I have both too much and too little area here. Do you see that box 1 is short some area? Definitely short, right? I'm missing some space. Box 3 was pretty good. Box 4 overestimates. Does everybody see that? So does box 5 in a big way. Do you see how much extra box 5 has in it? So I have both an overestimation and an underestimation when I do a left Riemann sum, depending on whether the function is increasing or decreasing at that point. If I'm doing a left Riemann sum and the graph is increasing, then I will be underestimating the area. If the graph is decreasing, a left Riemann sum will overestimate the area. Does that make sense to everybody? Okay. But if I add them all up, will this approximate the area under the curve? Okay, now this they knew about for hundreds, well, thousands of years. I mean, let's be honest, Chinese were doing this back in 5000 BC, right? Truly they were. In fact, they got quite accurate values for doing processes like this. But the next step is the one that made it possible to find the precise area under the curve. What do you think they did in the late 1700s, Newton and Leibniz separately? What did they do once they created this idea, this concept of the limit? What did they do to this process?
Delta x goes to infinity.
Delta x doesn't go to infinity. You're right, something goes to infinity, but delta x goes to what?
0.
Delta x goes to 0. What goes to infinity? N goes to infinity. When delta x goes to 0, each box gets narrower and narrower, which means you need more boxes, right? More boxes, n goes to infinity as the width of each box goes to 0. So what they were able to show was that the true area under the curve between A and B is going to be the limit, and you can write it two ways, as delta x goes to 0 or as n goes to infinity, because those mean the same thing, of the sum of each partition, sum of the area of each partition. Does that make sense to everyone? As the boxes get narrower, you have to have more boxes, right? And they've got to get closer and closer together. Now, when you're doing the formulas, remember I said we tend to give these guys names, so let me put up the names so that you'll recognize them, because we're going to be doing a right Riemann sum as well. We usually call point A x sub 0, all right? The next one would be x sub 1, x sub 2, x sub 3, x sub 4, all the way up to the last one you use is x sub n minus 1. That's the last one you use for a left Riemann sum. But what would B be? X sub n. So point A is x sub 0 and point B becomes x sub n. Let's repeat the process, but let's use the right side instead. Can I do that? Sure. So if I'm going to use the right side, that means that I will not ever use x sub 0 for the height of a box. What will I use instead? I'll use the right endpoint, which would be x sub 1. So a left Riemann sum only uses x sub 0, x sub 1, all the way up to x sub n minus 1. But the right Riemann sum is only going to use x sub 1, x sub 2, x sub 3, and it does use x sub n. It uses B, as you might imagine, because you're going to use the right side to draw the box instead of the left side. Now the process is reversed. If you're doing a right Riemann sum, am I overestimating or underestimating that area? I'm overestimating. So a left Riemann sum and a right Riemann sum sort of over and underestimate in opposite situations. So the left Riemann sum is an underestimate when it's increasing, but the right Riemann sum is an overestimate when it's increasing, right? So the right Riemann sum basically just uses the right endpoint instead of the left endpoint. This box isn't really all that much different. But when I get over here, notice that where this box is decreasing, I am way under in my area. I'm missing an entire sliver right here, okay? So you have the left Riemann sum and a right Riemann sum, and we'll do an example of one of these in just a second. Now, this is sort of where they started. The next question, of course, was, how can I make this a better approximation? besides letting the width of each box go to 0 and the number of boxes go to infinity, could I get a better approximation maybe by picking a different spot? So they've picked the left side, they've picked the right side. Where would you pick next? If you were going to pick, where would you pick? If I had to pick a spot in here, they picked the left side, they picked the right side, where could you maybe like average out this over under? In the, pick the middle. So that's the next one, which is the midpoint Riemann sum, which your book kind of skips, which is bad because it's a better approximation. We will not be skipping it. You will be doing it. Okay, so then we have the midpoint Riemann sum. So what does the midpoint Riemann sum do? We need another color. The midpoint Riemann sum says, okay, the left and the right Riemann sums are either overestimations or underestimations. So maybe if instead of picking the sides of the box, if I pick the midpoint of the box, right in the middle, and I take that F value, I'll be a little over on one side and a little under on the other side. Does everybody see that? The midpoint Riemann sum is in general a better approximation than the left or the right, typically, right? That's not true for all functions, but on average it's true. It's not necessarily true for any specific function, but in general, the midpoint's a better one, right? Now, in order to do a midpoint, we need to figure out how we can calculate those midpoints. So how would you write down how to find that point? How can I write down what these x values are that I'm using? For left and right, it's not difficult. Left uses x sub 0 up to x sub n minus 1. Right uses x sub 1 up to x sub n, which is b. But how are you going to tell me how to calculate the midpoint of each interval? I mean, you could crunch it out by hand, right? I know you could all do it. You take a plus x1 divided by 2. That would do it. But can we come up with a formula that does it a little bit better? And the answer is, well, no, not really. You really can't. So what you're going to do is you're going to take x sub n minus 1 plus x sub n and divide by 2. That's the point that you're going to use to calculate the height or the length of the rectangle. Okay? Does that make sense to everybody? There really isn't a better way of doing it. Okay? You're just going to have to do the 2. But it is a formula, right? You don't have to actually go through. You can compute a formula. Now, a lot of times these are done on computers and calculators because that's the best and easiest way to do it. It's a very repetitive process and it's a lot of number crunching, but it's mostly arithmetic, right? I mean, this is just arithmetic. Add 2 numbers, divide by 2. A little bit of algebra, take that number and plug it into the function. That gives me the height of the box. And then more arithmetic, multiply the length times the width. Now go to the next box and repeat the process. So it's just a lot of repetitive processing. So let's do an example of one. Let's put one up here. And I'll show you exactly what it comes out to be. All right, I think we'll leave that there. So let's look at the function f of x equals 1 over x on the interval from 1 to 5. And to make it doable in a 1-hour class, we'll just take 4 boxes, all right? Because the more boxes you have, the more arithmetic you've got to do, all right? It takes a lot of arithmetic. Okay, first off, in order to do this, remember you're trying to find the area between the curve and the x-axis between 2 specific x-coordinates. Those 2 specific x-coordinates are given as a closed interval. That means that A is 1 and B is 5. So the first thing we're going to do is we're going to write down A is 1 and B is 5. And I have to tell you how many partitions to make, how many different cuts to make in the graph, or how many different shapes to make out of it. So if n is 4, I want 4 boxes, how wide is each box going to be? So I left the formula up over here. How would you find the width of each box? I mean, aside the fact that you can just look at it and tell, what is it? 5 minus 1 divided by 4, which is, they're 1 wide, all right? So the next thing I'm going to do is I'm going to draw a picture of this graph. So here's the origin. This is 1, and let's see. 1, 2, 3, 4, 5. It does help to make the pictures bigger so you can kind of see what's happening. When x is 1, what is the function value? Just plug it in. 1. So I'm just plotting points right now. When x is 2, I get 1/2. So that would be right about there. When x is 3, I get 1/3, which would be about there. When x is 4, I get 1/4, which should be about there. And when x is 5, I get 1/5, which is about there, maybe a little lower. In other words, this is the graph that does this, right? And it approaches the x-axis as x goes to infinity, right? And it has another piece over here, but I'm not interested in that piece. I'm only interested over here. I want to know how much area is under the curve between these two x-coordinates, x equal 1 and x equal 5. This region right here. Now you need to be very careful as we move forward into integral calculus that when you're trying to find the area of a region, that the region is completely trapped. And by what I mean by that is, imagine that this line forms a boundary, the two vertical lines form a boundary, and the x-axis forms a boundary. So that if I poured water in here, it would hold water. Does that make sense? The water wouldn't leak out any side because it's completely bounded by those 4 sides, right? When we get a little bit further, you'll see what I mean. If you draw it in the wrong region, it won't hold water. For example, if I poured water over here, the water would just kind of come out this way because I never said the y-axis is one of the boundary lines. I said the function, the x-axis, x equal 1, and x equal 5. Nothing else counts as a boundary, all right? So if I poured water here, it would just go out that way, right? It would flow out. So if we're going to find the area here, what we need to do is draw our partition lines, which look like this, and we'll calculate each one. So if I'm looking at this one and I want to do the left endpoint Riemann sum, sometimes we will call the point that we want to calculate it at, we'll put a bar over it. I don't remember if your book uses this notation or not. But in order to calculate these, the ones that you want for the left Riemann sum is you always want the one on the left side, right? So you want n minus 1, basically. This x bar, which ones do you use? Use the left side, one less than what you're going to, all right? For a right Riemann sum, what would you use? X bar would just be the right side, right? X sub n. And for the midpoint Riemann sum, you're going to add, x bar would be x sub n minus 1 plus x sub n divided by 2. Add the two together and then divide by 2. All right? So let's do the left Riemann sum first. This is a decreasing function, so it's going to be an overestimation of the area. All right? Here's my first box, which I don't want to fill it all in. So what's the area of the first box? The width of every box is 1, and since it's a regular partition, that means every box is the same width. So could I factor out the widths of all the boxes in one go? Because this should be delta x times f of x sub 0 plus delta x, move over, times f of x sub 1 plus delta x f of x sub 2 plus delta x f of x sub 3. And I'd stop there because the left stops at one less than the number of boxes, number of partitions. Does everybody buy that? Every one of these has a delta x. So I could factor the delta x out. It's 1 in any case. And this just gives me the sum of the heights of the boxes. And what would that be? Let's fill them in. What's the height of the first box? 1. What's the height of the second box? This one right here. 1/2. Third box. Oops. Yep. Third box is height 1/3. And the last box. 1/4. Now you're going to have a common denominator, or you need a calculator, whatever you're going to do. But if you crunch out the numbers, you should end up with 25 divided by 12, which is about 2.083 bar. Okay? Is everybody with me to there? Does that make sense? It's a pretty straightforward process. Let's do the right Riemann sum.
For the x bar that you wrote under the left Riemann sum, is it supposed to have that little n in the bottom?
Oh, that, no, sorry, my bad. I was thinking of the other. Good catch. Okay, let's do the right Riemann sum. Right Riemann sum, we're going to do our area. We're going to factor out the delta x because they're all the same width. But this time I'm going to use the right endpoint to make my box. So it would look kind of like this. Second box would be kind of here. Third box would be here. And the fourth box would be here. Right? Because it is a decreasing function, the right Riemann sum is going to underestimate the area. Does everybody see that? It's going to be an underestimate. So I need now f of x1, f of x2, f of x3, and f of x4. Because the right Riemann sum uses those subscripts. It does use b. The left Riemann sum uses x equal a, but doesn't use x equal b. The right Riemann sum does not use x equal a, but it does use x equal b. Midpoint doesn't use either one, right? It takes the middle of every box. So what do you get for this? This would be about 1 times, what's the height on the right side of the first box? It's the left side of the second box for the left Riemann sum, right? What's the height here? 1/2. Plus the next one, 1/3, right? Because I'm now at 3. Plus 1/4. And then plus, what's the height at the last one? 1/5. All right. And I don't think I did that one ahead of time, so I need a calculator. One of the reasons I like the sharp right view so much is it automatically reduces. I have 0.5 plus 1 divided by 3, 2. That is 77/60. Which is about, well, it's exactly 77/60, which is about 1.283 repeating. Somebody tell me where the true value for the area has to lie. In between the two, all right? Let's do the midpoint Riemann sum now, all right? You can see there's a lot of number crunching in here, right? Lots and lots of number crunching. Okay? Clearly this one is too low and this one is too high. So it's kind of like the three bears. Let's try the one in the middle. Okay, so let's do the midpoint. So if I'm going to do the midpoint Riemann sum, what is the midpoint of partition 1 or interval 1? What's halfway between a 1 and a 2? Now you can do it either way you want. In this particular function, I recommend fraction form, because dividing by a fraction is the same as multiplying by the reciprocal. So I'm going to write this as 3 halves. And what's halfway between 1 and 2? I mean 2 and 3. 5 halves. Do you see a pattern here? What's the next one? 7 halves. What's the next one? 9 halves. And if I'd gone further, it's 11. It's all the odd multiples of 1/2, right? So there's a pattern. So now to do the midpoint, my area is going to be about, all of them still have delta x. But now what I have is f of x sub 0 plus x1 divided by 2 plus f of x1 plus x2 divided by 2 plus f of x2 plus x3 divided by 2 plus x3 plus x4 divided by 2. All right? Working all of that out, I get, well, I'm going to plug it into the function, which is 1 over 3 halves. And the next one is 1 over 5 halves. 1 over 7 halves. And 1 over 9 halves, which we decided meant this is 2/3 plus 2/5 plus 2/7 plus 2/9. Is this going to be a better approximation? What do you think? Yes or no? Yeah, it's going to be a way better approximation. So on this particular one, if you crunch all those numbers out, you will get, I will not make you do it. I recommend something like the Sharp Right View, or your graphing calculator can do it. It's not as good, but it will work. And you will get 1.57. Is that between these two?
Yes.
It is between those two. All right? Does that make sense? Now let me draw the boxes so you can see the boxes. So this one again is going to take the midpoint for the height of the box. So it's a little too short on that side, but a little too high on that side. So it's getting both a little over and a little under on each box. It's kind of averaging out the error, if you will. It's a little over and a little under. Now, if we hadn't had so much snow this week, we would have been doing all this in 2 different days instead of all in 1 day. But now I want to introduce you to the idea of the definite integral, which is in 5.2. All right. So we'll do just a little bit of 5.2 today, just enough for you to understand how it relates to the Riemann sums. So the question is, if I'm going to get the true area under here, then I have to make the width of each box smaller and take more boxes. As I take more boxes, I'll get a better approximation. I'll show you in a second what the picture looks like. It turns out that if you allow the limit of the width of each box to go to 0, you get what's called the definite integral, right? For a definite integral, you're going to take the indefinite integral of the function And you're going to put numbers on the integral symbol itself. And the numbers represent A and B. And that A, the one at the left, goes on the bottom, and the B, the one at the right, goes on the top. Now, a definite integral is a completely different animal from an indefinite integral. When you do an indefinite integral, the antiderivative, what you're doing on Monday on the exam, you give me a function up to a constant that represents the antiderivative of the integrand, all right? The definite integral takes that function and computes the area between it and the x-axis, between x equal 1 and x equal 5. So the indefinite integral gives me the antiderivative function. The definite integral takes that function and computes the area between it and the x-axis. All right? How do you do that? You use the indefinite integral. How would I convert this into a form that's more easily integrated? X to the negative 1. Put it in power form. So I'm going to write this as x to the negative 1 dx. I'm ignoring the 1 to 5 for right now. Now undo the power. So how do you undo? Oh shoot, I picked a bad one. Okay, I can't do that here because what would happen? I picked a bad example. I'd be dividing by 0, right? Okay. How else can we do this? Oh, well, you know what it is, right? What function has a derivative that is 1 over x? It's natural log. So this should give you natural log of x up to a constant, right? The question is, what do you do with the 1 and the 5? And the answer is, I need to compute the area under the curve. And the way you do that is you put a long vertical bar, and you're going to evaluate that function between 1 and 5. Which means this. First, I'm going to take the upper limit, and I'm going to plug it into the antiderivative function. Natural log of 5 plus a constant. And then I'm going to take it and plug the lower limit in, natural log of 1 plus a constant, and I'm going to subtract the lower one from the upper one. What happens to the constant every time you do that? The constant will drop out. It does not matter if it's natural log or some other function. The constant will always disappear. Do you see that? If you plug in the upper limit and you have this plus c, and you plug in the lower limit, I left my 1 off, didn't I? And you still have this plus c, and then you subtract the lower one from the upper one, you've got c minus c. So when you do the definite integral, do you really need the c? You never need the c when you do the definite integral. It will always disappear. And I end up with the natural log of 5 minus the natural log of 1. What is the natural log of 1? 0. So what is this? It's the natural log of 5. How much is the natural log of 5? It's about 1.609. I got 2 something with the left Riemann sum, 1.28 something with the right Riemann sum. I got about 1.57 with the midpoint, but the exact area under that curve is the natural log of 5 square units, which is about 1.6. And you can see that the midpoint was a better approximation, which is typical. Right? Does that make sense to everybody? What the Riemann sums are. Your last Python project, when I have a conference the second week of November, which I knew a long time ago, so I planned for it. What we'll be doing, or what you'll be doing while I'm gone, is doing 2 different kinds of approximation. right? We've done the left, we've done the right, we've done the midpoint. There are two others that are commonly used. Part of what's making this a problem to approximate the curve is that the top is flat, meaning horizontal. Could I get a better approximation if I didn't require it to be flat? So you'll be learning two other techniques. And one of them is called the trapezoid rule. So instead of connecting with a horizontal line, connect it with a straight line. Now why is this a trapezoid, right? So a trapezoid would connect like that. Do you see how much closer to the true area the trapezoid is? I wouldn't say it's always a better approximation. Actually, the midpoint is surprisingly accurate, especially when you have not very many boxes. But the trapezoid gets closer if you have more boxes. So the trapezoid, what makes a trapezoid? Most of the time we think of a trapezoid shape as looking like that. And the rule for a trapezoid is you have precisely one pair of parallel sides and the other two are not parallel, right? Okay. The fact of the matter is this is a trapezoid. It's turned sideways, so it's tilted up on end. These two sides are parallel, right? But that side is not parallel to the base. So this is considered a trapezoid where I just sort of took this shape, I cut off one end of it like that. So this is still a trapezoid, and then I took and I rotated it up. And that's what I have here. For the trapezoid rule, to find the area of a trapezoid, you have to average the two bases that are parallel to each other. So you add that length to that length and divide by 2. All right, so your height will be an average of the two sides. All right, instead of averaging out and using the midpoint, instead of averaging the width of the box to find x sub n, or x bar, what you're doing instead is you're averaging the height of the box, okay? Now there's another one called Simpson's rule, which goes one better and says, okay, maybe we shouldn't be using straight line segments because most of our functions are curved, right? I mean, it's curved, it's not flat. So instead of using a flat side, let's approximate between here and here using the best parabola that connects those 2 points. And you end up with shapes with parabolic tops, okay? That's called Simpson's rule. And it turns out you can actually compute that using nothing more than algebra, but the formulas for Simpson's rule are pretty complicated, which is why I do not want you to do it by hand. Because if I made you do it by hand, one problem would take you probably 45 minutes to an hour just for one problem, which is just, it's a waste of your time. So what I'm gonna have you do instead is you'll program it, and then you'll use it to evaluate the area under a curve and decide which one's a better approximation, okay? Let me show you what it looks like when you get more boxes.
Sorry.
Yeah.
I'm struggling to visualize how we just use the antiderivative of the function to estimate the area.
To estimate the area. Okay, so let me show you where it comes from. And we'll be talking more about that next week.
Oh,
all right,
okay.
so that's part of what will be coming next week. We'll be doing a lot more of that. I just want to introduce it today, but I'll do another example for you. Let me show you what it looks like when you get more and more boxes under here. So it turns out if you took something, let's say I did another example. Let's just take the very simple x squared function, right? And I were looking at x squared, and let's say I went from 0 to 2. So this would be at 2, 4. If I want to know how much area is right there, I need to integrate from 0 to 2 These have to be x values because that's an x value. And this represents that vertical line and that vertical line. Then I do the antiderivative, which would be x to the third over 3, evaluated between 0 and 2. So I would plug this into the top one. That would give me 8/3. Well, if I plug in 0, what do I get? So what's the area underneath there? It's 8/3. 8/3 square boxes, each box being 1 by 1 in size. That's exactly how much area is under there. So if they were square feet, I could tell you precisely how much paint you need to paint it. Okay, that's exactly what it is. Right? Let's take a look really fast at some of these on here. Would you call this a left Riemann sum, right Riemann sum, or a midpoint? They have to be Riemann sums because they have flat tops, right? Boxes. Left, clearly the left. Do you see that I've lost some area here and here? Yeah, I'm really low, right? What would happen if I increase the number of boxes? This is the same curve. It's a little less area. I'm still short. How much area am I? I'm still short, right? I can't hardly tell I'm short there. I'm still short a little bit, but am I getting closer? So as you allow the width of each box, the boxes themselves are getting narrower and narrower. So delta x is going to 0, but the number of boxes is going to infinity. So n goes to infinity, delta x goes to 0. It says the same thing. As you do that, it gives you exactly the area under the curve. That's what the definite integral does, right? It's exactly what the definite integral is. Now the definite integral actually has a definition which I haven't given you yet. I'll give it to you on Tuesday. I skipped over the summation notation because I wanted to get you the understanding of it. We'll come back and do summation notation next week, all right? Because I know that's something that probably some of you have never seen before. Just so I have a feel for where this class is, how many of you have done summation notation before? And by that I mean, you know what it means if I write that. How many of you have not seen this before? Okay, how many of you think you have done it before? Okay, so it's probably maybe a few more that have not seen it. Okay, all right. So I'll allow in the schedule to spend more time on this because I know at least half of you have never seen it before. This is used in the definition for this, right? Which is how you can use the antiderivative to come up with the area under this curve, right? Okay, so I'm going to stop here for today.